Well, thank you, Chris, and thank you to your whole team for putting on this remarkable day. The Rare Disease Day gets bigger every year, and this year is just absolutely amazing, the number of ideas and people and presentations and ways to work together that are happening across multiple different disease conditions and scientific areas, all of that in the course of today. And I hope many good things will come out of this that will have consequences going forward. That's certainly what we had hoped to achieve by bringing everybody together, raising awareness. I can tell you that the awareness of the importance of rare diseases is steadily growing. It's certainly growing at NIH, where virtually all of our 27 institutes and centers have some investment in rare disease research. And they see it as a remarkable moment scientifically to make progress that most of us didn't really quite dream could happen in this kind of time frame, but now it is. And I hope you're getting a sense of that today in terms of the trajectory of forward motion in being able to understand how to diagnose and treat these 7,000 disorders that we call rare diseases. We have a long way to go. We still don't have treatments for nearly enough of those, but the path forward seems now to be clearer than it has been, at least in my perspective, over the last 30 years. And the ability to begin to tackle things, many diseases at a time, as Chris would say, where instead of trying to have a complete focus on just the minutiae of every single disease, we figure out how to bring together approaches that can be scaled and that can tackle multiple diseases without the need to have quite, therefore, the same long timelines and deep need for resources. Also tell you that the Congress of the United States is increasingly aware of and sympathetic with the importance of NIH spending money on rare diseases. Many of us were on the Hill on Tuesday night for a reception that was sponsored by the Children's Inn. And of course, many of the kids at the Children's Inn have rare diseases, including the family that was there and that was featured, a wonderful family from Missouri whose son, Abram, has one of these autoinflammatory diseases that very day had just received some new information from a DNA analysis that might indicate what the diagnosis was. And at that reception on Capitol Hill, there were about 20 members of Congress who turned up. They were from both parties. They were from both houses. We had presentations and speeches made by 4 members. And the unanimous sense you had was that this is one of those rare issues that our Congress agrees on, which is medical research is a valuable investment by the federal government, and rare diseases is a valuable part of that. So I hope you feel some encouragement by that, given how in many other ways what's going on in this town seems so dysfunctional. Nobody disagrees that this particular area is going really exciting directions and is remarkable in terms of its promise and is worthy of support. And I can tell you from my perspective as the NIH director, because I do get the chance to talk to members of Congress quite frequently, it is often a rare disease that I start out with, trying to tell them a story of a circumstance where something that used to be really impossible to understand is now yielding up those secrets, and treatments are emerging for kids and adults that we previously didn't know what to do for. One that I talk about a lot right now is sickle cell disease. Sickle cell, maybe not as rare as many of the conditions that you all represent, but still only 100,000 people in this country. And you are going to see in the next few months, I think, increasing numbers of reports where genetic therapy applied to this first molecular disease, described more than 100 years ago and known to be due to a single misspelled letter in the genome. Those therapies are starting to work, not just as treatments, but as cures. Watch 60 Minutes sometime this month of March, and you'll see a pretty dramatic example of how that is coming forward. And I'm really excited about that because, as I just tried to say a minute ago, the approach that was taken there is one of those which could fit other diseases as well, a genetic approach. When we see that happening for sickle cell disease or for spinal muscular atrophy, and maybe soon muscular dystrophy, the excitement of having that kind of outcome cannot be overstated, but particularly so when we see that that strategy might then be applied to hundreds of other disorders. That's one of the things we at NIH don't want to miss the chance to see and to encourage. NCATS is very much in that mindset and leading many of us to think about it in that way, the many diseases at a time. Another program, though, that I want to mention to you is one funded by the Common Fund, which is the part of NIH that represents our venture capital space, where we can try out things that are high risk but potentially high reward that no single institute would have had the resources or the motivation to tackle. But if they succeed, it could in fact have an impact on many different diseases and across all of NIH. As we've seen the promise of gene editing using this remarkable system called CRISPR-Cas and other things like that, it does seem like we are at a real juncture here of opportunity to bring that into therapeutic places that previously haven't been reachable, to go right to the heart of a genetic disorder. And instead of trying to correct the consequences in terms of the symptoms or the abnormal protein that gets generated or the RNA that's misspelled, let's go right to where the fundamental misspelling is in the DNA and see if that is possible to do something about. And that is what is happening now for a few conditions in the research arena. And again, sickle cell is one of them, Duchenne muscular dystrophy is another. The real challenge there, though, is going to be if you have a disorder that affects some part of the body that you can't very well take the cells out and treat them and put them back. You have to do this actually in what we would call in vivo. How do we come up with a system to deliver the apparatus to do that elegant kind of search function to find the misspelling and fix it in somebody safely and effectively? And that would be called in vivo gene editing. We now have a whole program, $190 million going into it. The first meeting of the investigators just happened a couple months ago, called the Somatic Cell Gene Editing Program. Again, somatic cell, let's be clear, we're not talking about embryos here. We are not in the business of modifying human embryos for purposes of reproduction. But if you have a genetic disorder and you know it affects the liver or the brain or the muscles, and you have a means of delivering very efficiently this apparatus with the corrected opportunity to fix that misspelling, that seems like something that could be scaled. That's what this program is about, the Somatic Cell Gene Editing Program. You're going to be hearing, I think, more about that in the next year or two as this group comes together and tries to figure out how to achieve that very challenging delivery problem in a fashion that's safe and effective, obviously starting with animal models, but quickly as we can, moving towards human applications. So I guess whenever I come to a conversation about rare diseases, I do often think about ways in which progress has been made, and it's, of course, the nature of almost all of us to think particularly about conditions that we've had the chance to work on and people who have influenced us by the way in which they, courageous folks that they are, have taken part in a wide variety of clinical applications, not all of which have worked and not all of which we're proud of, but all of which were circumstances where we agreed with our participants to try to tackle something difficult. In my blog today, I'm sure you all read my blog every Tuesday and Thursday. I write about a courageous young woman with Job syndrome, Harper Sparrow. If you go to NIH website and just go to the director's page, you can pull up this story. And she, under the care of Alexandra Freeman and Steve Holland here in the intramural program at NIH, has gone through an amazing series of experiences, but has made it her task to teach the world about this. And her podcast called Made Visible tells stories about herself and others with rare diseases. So have a look at that blog. Job syndrome is not called Job syndrome for ideal reasons. This is Job of the Bible, so you can imagine somebody with that syndrome must be going through pretty amazing series of stresses as she has, and yet she is using her experience to teach others. Have a look at Harper Sparrow. And I do want to say congratulations to the winning entries in the creative effort to raise awareness. The artwork and the Rare Diseases Are Not Rare challenge. I looked at all of those. Those are pretty phenomenal. I was also over in conference room C, if you have not been there, and looked at the portraits of kids and young adults with genetic disorders and other rare diseases as part of the Beyond the Diagnosis program that Patricia Welton and her team have brought here. If you haven't wandered into conference room C, go and look at those. They're really quite inspiring, quite moving, quite beautiful in the way in which they portray the reality of what kids with these conditions are. They're not defined by their diagnosis. They're all clearly kids with personalities and a lot to contribute. Again, when I think about rare diseases, I do think about the opportunity that I've had now over the course of more than 15 years to work on one of the rarest, and that's Hutchinson-Gilford Progeria syndrome, the condition which causes kids who appear normal at birth to age at about 7 times the normal rate, and who, without intervention, die at age 12 or 13 of heart attacks or strokes, just like you'd expect of somebody in their 80s or 90s. And yet their intellectual development is entirely normal. If anything, it's exceptional. I had the chance to take care of a patient with progeria way back in the 1980s when I was a fellow in training, and I was assigned a patient who carried that diagnosis, and I was fascinated by the stories she would tell me. This was Meg Casey, about her experience, and frustrated that we knew so little about it. Meg Casey had rather single-handedly rendered her little town of Milford, Connecticut, accessible to anybody with a disability. Long before the Americans with Disabilities Act, there was Meg Casey in Milford, and she made sure that there was no establishment that could not be accessed by people with limitations such as hers. She was all of about 3 feet tall, but she could curse like a sailor, and you didn't want to mess with her. And so I thought at the time, boy, this is a disorder somebody ought to work on. I hope someday that happens. And then some 15 years later, at a reception here in D.C., I was at that time leading the Genome Project. I encountered a young man who was an emergency room physician, but he was doing a White House fellowship. And he said, I have a son with a rare disease that was just diagnosed, and you've probably never heard of it, but maybe you could point me in the direction of who might be able to help me. He said, my son has progeria. His son at that point was 3 years old. That was Sam Burns. His dad, Scott, his mom, Leslie, were both physicians, both very interested in trying to see what could be learned about this condition that their son had, which virtually not much was known. It seemed to strike like a bolt from the blue. There were no families with more than one affected child. None of the kids had ever lived long enough to have their own children, so we couldn't even determine what the mode of inheritance was. It seemed like it might be a genetic disorder, but there was no way to be sure. So I agreed to help them put together a workshop to try to get people interested in this condition, particularly aging scientists who might be, not because they were aging themselves, but because they studied aging, who might see this as a window into understanding a process that's not the rarest of all diseases, but the commonest of all experiences, namely that we are all aging. And that kind of worked, and a few people got interested. And then I got really interested, and I had a postdoc in the lab who was looking for a project, and we decided, well, let's just see if there's some way to figure out what this is. And with a combination of energy and serendipity and a really good postdoc, within the space of a year, we discovered that this was due to a single letter in the DNA code that was misspelled. And it was always de novo, that it arose for the first time in that child. The parents' DNA were normal, but every child we looked at that had progeria had this particular letter that should have been a C, and it was a T, in the middle of the coding region of a gene that was coding for a protein that was part of the nucleus, part of the structure of the nucleus. You know, the nucleus looks that beautiful oval structure. What holds it into that position? Well, this protein was a big part of that. That meant that we could go to school on all of the people who had studied that protein and pretty quickly figure out why this misspelling was causing the problem that it did. And in this instance, because there was all that information and it led us in the direction to try some therapeutics that had been developed for an entirely different purpose, namely for cancer. It turned out these cancer drugs hadn't worked at all for cancer, but they had the right properties to work for progeria. And within 4 years, after knowing the cause, a clinical trial got started in 2007. That clinical trial went on for 3 years and carefully looking at all the data. And now that we've got a lot more data because these kids have stayed on the drug, it's clear that this has extended their lifespan by at least 5 years. And that's enormously exciting. But it's not good enough because we want to see actually something that could result in a almost normal lifespan, because that's just how bold I think we all have to be in this circumstance. So now, as a follow-on to that, we're engaged with the Progeria Research Foundation. This is a collaboration like the model you heard described in the panel that came before, where we bring together NIH, we bring together some other academic researchers, we bring together Boston Children's Hospital, the Progeria Research Foundation, and biotech companies, in our case, Sarepta, working on a morpholino approach to this, where we're trying to affect the abnormal RNA and dial it back. And very recently, also moved into the area of gene editing, working with David Liu at the Broad Institute to try to see whether we could do the ultimate that I was talking about a bit ago, where you'd actually go in and correct that misspelling in the most vulnerable tissues in the cardiovascular system. Now, that is bold indeed, but it's not completely out of reach at this point. So I tell you all that because I think it's an example of the way in which, over the course of a decade and a half, things have happened that I could not have dreamed would be possible. And I want that to happen for all the conditions that you all represent here. And I think increasingly we can be optimistic that that is possible. But it takes a lot of energy, a lot of resources, a lot of commitment, which is what Rare Disease Day is all about. And I think as you all have the chance to get out there and tell your stories, you have powerful stories to tell. And we have a scientific moment right now that is ready to make this kind of rapid progress. If there was ever a time where bringing together rare diseases and scientific opportunity makes a compelling case, this is it. But it's particularly so when it's attached to real people. That's why I'm really glad this Rare Disease Day has that kind of focus. So I'll just finish then with saying a word about Sam Burns, because Sam, who was 3 years old when I met his mom and dad, was able to take part in those clinical trials and did in fact benefit from them. But I'm sad to say that we lost Sam at age 17 a couple of years ago. His mom and dad continue to be utterly devoted to this issue. There are probably only about 200 kids with progeria in the whole world, and they're all Scott and Leslie's kids now in their minds, and I guess their mind too, that we are devoted to finding answers for them. And I would just leave you with Sam Burns' recommendations about how we should all focus in this circumstance. I mean, here's a kid who had an awful lot of challenges and never lost his desire to make every day count. So Sam Burns' philosophy for a happy life, which I'd like to share with you. First, be okay with what you ultimately can't do, because there is so much you can do. Second, surround yourself with people you want to be around. Okay, we're doing that here. Third, keep moving forward. Well, that's absolutely what we are determined to do as part of this. And fourth, never miss a party if you can help it. This is our rare disease party. Let's have a great day today. Thank you all.